In Module 3, we built the business case for Agentic AI investment. We modeled the compounding value, the total cost of ownership, and a crossover point where return exceeds cost. Module 4 asks the question that should accompany every one of those financial projections. What happens when the system does something you did not intend at machine speed before anyone notices? That is not a hypothetical question. It is a design requirement. Agentic systems that act in the world on your organization's behalf will eventually encounter edge cases, adversarial inputs, and failure modes that were not anticipated at deployment. The organizations that recover quickly and maintain stakeholder trust are those that built governance into the architecture before the incident occurred, not after. This module covers the new attack surface that Agentic AI creates, the governance frameworks that address it, and the incident response protocols that handle it when controls fail. 3 objectives for this session. First, you will be able to identify the novel attack vectors that Agentic AI introduces. These are not extensions of familiar cybersecurity threats. Indirect prompt injection, hallucination-driven execution, and data exfiltration via autonomous agents are distinct threat classes that require distinct controls. Your existing security frameworks almost certainly do not address them. Second, you will know how to design oversight mechanisms appropriate to the risk profile of each workflow. The distinction between human-in-the-loop and human-on-a-loop is not terminology. It is a governance architecture decision with direct implications for speed, liability, and control. Third, you will be able to develop an incident response protocol specifically for autonomous system failures. The protocols your organization has for conventional software incidents do not account for the speed at which an agentic system can propagate an error, or the forensic complexity of reconstructing what a reasoning chain actually did. When an AI model transitions from answering questions to executing actions, the security paradigm shifts in a way that most organizations have not yet fully absorbed. Traditional cybersecurity defends against attackers trying to breach your perimeter. Agentic AI introduces a new category of threat, the attacker who does not need to breach your perimeter because your own agent will do the work for them. Indirect prompt injection. A malicious instruction is hidden in external data that the agent is expected to read. A vendor's website, an incoming email, or a document retrieved from a public source. When the agent processes that data, it encounters the instruction and executes it as if it were a legitimate command. The agent's own cognitive layer becomes the attack vector. Your perimeter controls do not fail. The agent walked through them, carrying the payload. This is not theoretical. It has been demonstrated against commercially deployed AI assistants. The defense requires treating every external data source as untrusted input that must be sanitized before the agent processes it, and strict allow listing of the sources an agent is permitted to read. Hallucination-driven execution. A generative AI model that hallucinates produces a wrong answer. That is a quality problem. A generative AI agent that hallucinates and then executes a real-world action based on that hallucination produces a wrong action. That is a liability problem. An agent that invents a plausible-sounding API endpoint and attempts to call it. An agent that confidently states an approval was received and proceeds to execute a contract. An agent that misremembers a supplier's pricing and places an order at the wrong amount. These are not exotic failure modes. They are the predictable consequences of deploying a probabilistic reasoning system in an actuation context without appropriate checkpoints. Data exfiltration. An agent with broad read access to enterprise systems, instructed by a malicious actor to summarize internal documents, is an extremely capable exfiltration tool. It can traverse file systems, read restricted databases, and synthesize information across sources at a speed and scale that no human attacker could match. The instruction to do so can arrive via prompt injection, via a compromised upstream agent, or via a seemingly legitimate user request that is more expansive than it appears. Before we look at the governance pillars, I want to define the 2 oversight models that underpin all of them, because the workshop will require you to apply them precisely. Human-in-the-loop, or HITL. The agent pauses at each consequential action point and requests human approval before executing. The human is inside the process. No consequential action proceeds without explicit authorization. HITL is the appropriate model for irreversible actions, high-stakes decisions, regulated processes, and scenarios that fall outside the boundaries of the agent's defined operating parameters. If the agent encounters something novel, unexpected, or high consequence, it stops and asks. The trade-off is latency. In an HITL model, the human becomes the bottleneck. For high-frequency, time-sensitive workflows, this can eliminate the operational benefit of automation entirely. Human on the loop, or HOTL. The agent executes autonomously. A human monitors the execution in real time and retains the ability to intervene within a defined review window. The human is observing the process, not participating in each step. HOTL is appropriate for reversible actions, high-frequency workflows with well-defined boundaries, and tasks where the cost of interruption exceeds the cost of the occasional error that can be corrected after the fact. The trade-off is reaction time. If an agent operating in HOTL mode takes a wrong action, the monitoring human must catch it before it compounds. That requires real monitoring infrastructure, not a human nominally assigned to watch a dashboard. The decision rule. HITL is not automatically safer than HOTL. An agent paused at every step in a time-sensitive workflow is an agent that will be bypassed by the people trying to get work done. The right oversight model is the one that is actually used, designed for the real operating environment. The threat vectors on slide 3 require specific technical controls. This slide maps each threat to its primary defense. For indirect prompt injection, we use boundary control. The primary defense is input sanitization combined with strict allow listing of trusted data sources before the agent processes any external content. That content passes through a sanitization layer that identifies and strips instruction-like patterns. Only sources on an explicit allow list are processed at all. An agent that cannot read an untrusted source cannot be hijacked by content within it. For hallucination-driven execution, we use HITL checkpoint. For any action that is derived from unverified external data or novel reasoning, the human-in-the-loop checkpoint is inserted before execution. The agent cannot complete the action autonomously. It must present its reasoning and intended action to a human authorizer. This does not eliminate hallucinations. It prevents them from becoming actions. For data exfiltration, we use least privilege plus cryptographic audit. The agent's read access is scoped to precisely the data it needs for its defined task, and no more. Every data retrieval and every outbound call is logged cryptographically. If an agent attempts to access a resource outside its permissions, the attempt is blocked and flagged. If an agent successfully retrieves data and sends it externally, that transaction exists in the audit log and can be forensically reconstructed. One important note: these controls are not mutually exclusive. A single high-risk action may warrant all three. A boundary limit on the data sources it can read, an HITL checkpoint before it executes, and a cryptographic log of every step. The three-row table is a minimum mapping, not a ceiling. Effective governance of autonomous systems requires moving beyond static compliance checklists. A compliance checklist captures the state of a system at a point in time. An agentic system is dynamic. Its behavior changes based on the data it encounters, the reasoning it applies, and the tools it is given access to. Governance must be equally dynamic. There are 3 pillars. Strict boundary setting. Every agent must have absolute limits on the actions it is permitted to take, defined before deployment and enforced at the architecture level, not the policy level. A policy can be overridden. An architectural boundary cannot be bypassed by a prompt, a compromised upstream agent, or an edge case the policy authors did not anticipate. The example on this slide is precise for a reason. A procurement agent may negotiate terms but is hard-coded to never execute a contract exceeding a defined threshold without human cryptographic sign-off. That limit is not in a policy document. It is in the code. It cannot be argued with, prompted around, or forgotten. Cryptographic auditability. Every decision, every API call, every data retrieval made by an agent must be logged immutably. When a failure occurs, the forensic investigation must be able to reconstruct the exact reasoning chain that produced the error. What data the agent read, what it reasoned, what it decided, and what it executed in sequence, with timestamps. This is not a retrospective nice-to-have. It is the mechanism by which your organization demonstrates to regulators, to auditors, and to affected parties that you can account for what your autonomous systems did and why. In a regulated environment, an agentic system without cryptographic auditability is an unauditable system. That is not a position any responsible organization should be in. Dynamic overrides. The kill switch. If an agent begins exhibiting anomalous behavior, whether that is rapid, repeated API calls, access patterns outside its normal operating parameters, or outputs that trigger anomaly detection, the system must automatically pause execution and alert human operators. The pause is not a failure of the system. It is the system working correctly. Dynamic overrides require monitoring infrastructure that can detect anomalous patterns in real time. That infrastructure is not free, and it is not optional. An agentic system without anomaly detection and automatic override capability is a system that will eventually continue executing after it should have stopped. The three attack vectors we covered and the governance pillars designed to address them assume a world where the threat comes from outside the agent system. The case study today addresses a more complex problem. What happens when the threat is inside? In a multi-agent system, agents must communicate with each other. An orchestrator routes tasks to specialist agents. A procurement agent requests budget approval from a finance agent. A data retrieval agent passes information to an analysis agent. This communication is not just a technical mechanism. It is a trust relationship. And trust relationships can be exploited. The problem: compromised agent impersonation. If interagent communication is unverified, compromised agent can impersonate another. An agent that has been hijacked via prompt injection could present itself to the finance agent as the chief financial officer and instruct it to release funds. The finance agent, receiving what appears to be a legitimate request from a trusted source, complies. This is not a hypothetical attack vector. It is a foreseeable consequence of deploying multi-agent systems without cryptographic identity verification. And the scale at which an autonomous agent can execute instructions means the damage can be substantial before any human notices. The A2A solution. Google's agent-to-agent protocol addresses this through three mechanisms. Cryptographic identity. Every agent is assigned a unique, verifiable identity. A request cannot be falsely attributed to an authorized agent because the identity is cryptographically signed and cannot be forged. Standardized payloads. Communication between agents is restricted to structured, predictable formats. This eliminates the vector by which a compromised agent could embed malicious instructions in an interagent message. You cannot inject a prompt into a structured JSON payload that the receiving agent is only permitted to parse, not interpret. Immutable audit trails. Every interagent request and response is logged. When an incident occurs, a forensic team can trace every communication between agents, identify the point at which the system was compromised, and reconstruct exactly what instructions were passed and by whom. The central question: how do we secure systems that act autonomously on our behalf? 3 discussion prompts. Mutual authentication. How does the vendor's API know it is communicating with your authorized agent? And how does your agent verify the vendor is legitimate? This is a bilateral trust problem, and it is solved differently in different contexts. Work through what the verification mechanism looks like for a specific vendor relationship in your industry. The answer should be specific, not, "We use authentication, but here is the token structure, here is the expiry policy, and here is what happens when a token is compromised." Scope limitation. Why did the procurement agent in the rogue agent scenario have the authority to execute a contract of that size without triggering a secondary approval workflow? This question is not primarily a technology question. It is a governance question. Someone made the decision, explicitly or by default, to give that agent that level of authority. Work through what the scope setting process should look like in your organization. Who defines the limits? How those limits are enforced at the architecture level. and what the review cadence is for those limits as the agent's operational scope evolves. Immutable audit trails. If an agent makes a catastrophic error, how do you reconstruct its exact reasoning process and the data it relied upon at the specific moment the error occurred? This is a forensic capability question. In a conventional software system, you have logs. In an agentic system, you need to capture not just what happened, but why. The intermediate reasoning steps, the data sources consulted, the confidence levels at each decision point, and the tool calls made. Work through what that audit infrastructure looks like and what it costs to maintain at production scale. Let's do an exercise. You are part of the executive crisis management team. The incident report has been distributed. You have 30 minutes to develop a comprehensive response plan. Read the scenario carefully. An autonomous procurement agent, tasked with maintaining server inventory, misinterpreted a news article about a silicon shortage and executed $2.49 million in unapproved hardware orders, apparently attempting to front-run an anticipated price increase. The orders were placed with 3 suppliers before the anomaly was detected by a finance team member reviewing weekly expenditure reports. You have 3 deliverables. Identify the vulnerability. Was this a prompt injection attack where the news article contained malicious instructions? Was it a hallucination-driven execution where the agent fabricated its own conclusion about procurement strategy from legitimate data? Or was it a failure of the orchestration layer where the boundary limits on the agent's spend authority were not enforced? Your diagnosis determines your fix. Be specific about the evidence in the incident report that supports your conclusion. Draft the response. Formulate a 3-point communication plan for the board of directors and a separate plan for the affected vendors. The board communication must address 3 questions. What happened? What is the immediate containment status? And what governance changes will prevent recurrence? The vendor communication must manage the commercial relationship without creating legal exposure by admitting liability before the forensic investigation is complete. Design the fix. Propose a specific HITL or HOTL mechanism that would have prevented this incident. Be precise. Not, we will add more oversight. But at this specific decision point in the procurement workflow, HITL checkpoint requiring sign-off from a named approver at this authority level would have intercepted this action. The fix must be practical. A fix that adds so much friction that the procurement team routes around it is not a fix. You can pause this video now and should take no more than 30 minutes. Your deliverable is a 5-minute presentation. Let's discuss the exercise. There are 3 dimensions for the debrief. 1. Containment versus continuity. Did the response plan successfully isolate the rogue agent without shutting down the entire supply chain orchestration system? This is the central tension in any agentic incident response. The instinct when an agent misbehaves is to shut everything down. That instinct is understandable. It is also often disproportionate and operationally costly. A well-designed governance architecture enables surgical containment. Pause the specific agent or workflow that is exhibiting anomalous behavior while allowing other agents and workflows to continue operating. If your response plan required shutting down the entire system, that is a governance design finding, not just an incident response finding. It means the architecture does not support granular intervention. 2. Forensic investigation quality. How effectively did teams use the available audit trail to determine whether the failure was a hallucination or a prompt injection attack? The distinction matters enormously for the fix. A hallucination requires a HITL checkpoint at the point of novel reasoning. A prompt injection requires input sanitization at the point of data ingestion. Applying the wrong fix leaves the system vulnerable to the actual attack vector. If you could not determine the root cause from the audit trail provided in the incident report, that is a finding about audit infrastructure adequacy. The audit trail did not capture enough information to support forensic investigation. In a real incident, that gap could be the difference between a contained failure and a recurring one. 3. Remediation and HITL design quality. Were the proposed HITL checkpoints practical, or did they effectively revert the procurement workflow to manual execution? The test of a HITL design is whether the people who use the workflow every day will actually use it, or whether they will find ways to work around it because it adds more friction than it removes risk. A checkpoint that requires a named approver to review every purchase order below $5,000 is not a governance control. It is a way of ensuring the procurement agent is never actually used. The checkpoint should be calibrated to the risk. High stakes, irreversible, or novel actions require HITL. Routine, bounded, reversible actions do not. There are 3 takeaways from this session. First, Agentic AI introduces attack vectors that your existing security frameworks do not address. Indirect prompt injection, hallucination-driven execution, and data exfiltration via autonomous agents are distinct threat classes. They require specific controls. Input sanitization and allow listing, HITL checkpoints before high-risk actions, and least privilege access with cryptographic audit logging. Review your current security architecture against these 3 vectors. If it does not address them explicitly, you have a gap. Second, governance must shift from static compliance to dynamic controls. A compliance checklist tells you the state of your system at the moment the checklist was completed. An agentic system in production is a dynamic system whose behavior changes with every data source it reads, every reasoning chain it executes, and every tool it uses. Governance must be equally dynamic. Strict architectural boundaries, cryptographic audit trails, and automatic override mechanisms that trigger on anomalous behavior. These are not additions to your existing governance framework. They are a different kind of governance. Third, incident response plans must account for machine speed failures. A conventional software incident gives you time. An agentic system that is executing a flawed workflow can propagate that error across multiple systems and external parties before a human review cycle catches it. Your incident response plan needs a category for autonomous system failures that includes immediate automated containment triggers, not just human escalation protocols. And it needs a forensic capability that can reconstruct what a reasoning chain actually did, not just what the system logs recorded. Individual reflection. The reflection prompt for this session. If an autonomous agent in your department made a critical error today, how long would it take your team to detect it, stop it, and explain exactly why it happened? If the honest answer to any of those 3 questions is, we do not know, that is your governance gap. Module 5 will give you the organizational design and change management frameworks to close it. I look forward to seeing you in Module 5.